Okay, so on to the ocean and fresh water. We're almost done. Okay, so we obviously know that water is really important. Water is really important in chemistry because we do almost all of our reactions in water because it has very special properties. So you guys know all of these things. We're just going to kind of like put them on here. Okay, water, whether you believe it or not, actually for its molecule size has a very high melting point and a very high boiling point. So it has a high melting point and boiling point for its relative size. Okay, and that is because of those hydrogen bonds, of course. Okay, it's got hydrogen bonds. Those are really hard to overcome and to get it to spread out. And so those hydrogen bonds really kind of drive life on Earth. So it's got a high melting point and a high boiling point. It's got a high specific heat. It's hard to change the temperature. High specific heat, right? 4.18 joules per gram degree Celsius is a lot higher than like metals. Metals are almost always less than 1. Most substances are somewhere around 1, between 1 and 2, but water is 4.184. So it takes a lot of energy to change the temperature of water. Okay, it's also, and this is atypical, its solid is less dense than its liquid. Solid is less dense than liquid. And that's why ice floats. Most things, as they become solid, everything gets closer together and it's more dense. And that is not the case for water. And it is also very polar. That's why chemists like it, because it can dissolve all of those polar and ionic things. Okay. So these are the kind of properties that are really important for us on Earth. If it didn't have a high melting and boiling point, it wouldn't stay liquid most of the time and we wouldn't be able to drink it. And that's the problem on a lot of other planets, is that it's not at the right temperature. So like it's a very special compound. So water on Earth covers 72% of Earth's surface. Okay, so that's most of it, right? But only a little bit of it is actually fresh water. 97.2% of that water is found in the oceans. Okay. Of course, most of it's in the ocean, some of it's in lakes and rivers and that types of things. So our fresh water that we of course need to survive only comes from streams, lakes, and groundwater. And that's where we get our fresh water, unless we distill ocean water, which takes a lot of energy. Now, these sources are very limited in some places, not where we are, but places like California, Nevada, Arizona, they can absolutely have water shortages or freshwater shortages, which can cause lots of problems politically and ethically. So we do have to be careful with our freshwater sources, and hopefully we can find a better way to purify ocean water, because then we would have more resources for water. So ocean water, then, if we did want to try to purify it, this is the problem. Ocean water has a lot of salt in it. Of course, it is salt water. It has lots of ionic compounds. So it's about 35 grams of dry salt per kilogram of water, to kind of like put that in perspective. That's a lot of salt. Okay, so in order to actually purify it, it's going to be difficult to get. So like this is our representation. So this was the water. If we can get all of the salt out, then we would have nice pure water. Now, what is in that 35 grams? It's not all NaCl. Of course, a lot of it is. So we've got sodium, we've got chloride ions. There's some sulfate ions, magnesium, 2+, calcium, and potassium. And most of those are kind of listed over here, but these are what we're going to find most of in the water. So we can actually use these if we do purify it. The commercially obtained substances from ocean water that we generally use are, of course, salt, regular salt. We can also get bromine from it, and then we can use the magnesium if we can get it out of the water and then reduce it. Yes. Okay, so how do we do that? There's a couple different ways to do that. One is, of course, we could like heat it up and collect it, right? That's called distillation, because it would leave all the salt here. It would put all the water over here. So we could distill it. Still. The other thing we could do is, and you might have heard of this, this is very common right now, is reverse osmosis. It's getting it to like filter kind of in a specific way. So if we distill it or reverse osmosis, both of these are pretty expensive in order to do on that large of a scale. But if we can, we could probably get some more water out of it. So I'm going to switch gears now to fresh water then. The fresh water that we do have, an average person uses about 300 liters a day, or that's like 80 gallons a day for consumption and hygiene. I'm like, that sounds pretty accurate if I take a shower and cook and use the bathroom and all of those things. So that's about how much water that we use a day. Now, of course, agriculture and industry use way more than that of our fresh water. So agriculture, of course, is extremely important, as is industry. But if there's a way to kind of cycle that back, that would be really great. So this is where our fresh water actually comes from, the water cycle that you learned about probably in like middle school. That's how we get all our fresh water cycle. That's this guy. No, I'm not going to ask you questions specifically about the water cycle, but I really just want to reiterate that fresh water is an important natural resource, sometimes that we take for granted. And hopefully we can find some ways to maybe purify ocean water. So we've got some more fresh water. Excuse me. Okay, so oxygen in the water is the next thing that I want to talk about. So dissolved oxygen in water. So this picture, which is kind of hard to see in black and white, is essentially like a zoomed in portion of the water cycle. We've got runoff going back into the water. And what I want to look at or talk about now is the amount of oxygen in the water. So there's like O2 down here. We can get things like algal blooms, which can cause eutrophication, which is like death of everything. And so this is also a very delicate balance, just like the climate, the water itself is. So the oxygen in there, what we need is of course dissolved oxygen, because there's animals and things that live in the ocean, they need oxygen as well. So life in the water depends on dissolved O2. Okay, and water at 20 degrees Celsius, which is a pretty typical temperature. So 20 degrees Celsius, it can hold about 9 parts per million of oxygen. Okay, so that's not a lot, but it is enough to sustain life. Fish need about 5 parts per million. Fish need about 5 parts per million. Okay, so as the temperature of the ocean increases, that also causes oxygen not to be as dissolved, which can cause fish to die. But they do need about 5 parts per million. Now, the fish kind of battle it out with algae and bacteria who also need oxygen. And that's where we can have some issues occur. So bacteria and algae also compete for O2. So when we have bacteria and algae that kind of like get a little bit too excited and reproductive and they make lots and lots more algae, we get these things called algal blooms, and they cause eutrophication. So eutrophication happens when we have like too many nitrates and phosphates. It just kind of promotes algae growth. So this is spurred by nitrates and phosphates. Okay, and we haven't talked about nitrates and phosphates today specifically, but those can come from pollution as well. So the more polluted the water is, we might kind of cause more algae and bacteria in the water to grow, which negatively impacts the wildlife that we want, like fish. So there's actually some spots where this like consistently happens. This is right under Louisiana. Okay, this is the Louisiana shelf. And the oxygen levels are very low here. So the fish cannot exist. So this is wide scale eutrophication. So eutrophication is death of all plants and fish. Okay, and this actually happens when rivers are emptying into the oceans, which is why we see it down here where there's multiple rivers that empty into the ocean. So happens where rivers empty into oceans.
So wait, in that like whole area, there's like no fish at all?
Yeah, so it's kind of a little bit further off coast than like what it seems here. But it's the bottom oxygen. So there might be some on top, like some fish closer to the surface. But closer to the bottom of the ocean, we've got like nothing going on down there. Excuse me. Yeah, if you look at these numbers, as it gets red, that's less than 2 parts per million of oxygen. That's not enough to sustain anything. So we'll get all that algae and bacteria, but that's about it. Okay, so onto water that we drink, and that is municipal water. Water in our homes originates, and I already mentioned this earlier, this comes from lakes and streams and groundwater, lakes, streams, and another word for groundwater are aquifers, so underground aquifers. We actually sit on top of, or pretty close to, on top of a very large aquifer, and that's where we get a lot of our water. My hometown is like right over one of the biggest aquifers in the Midwest, which is kind of cool, but that's where we get a lot of our drinking water. Now, of course, it's a very complicated process to get it so that we can drink it. This has always been kind of interesting to me. My dad actually works as an engineer and has like goes to lagoons and stuff to check on how the water is doing. But if you look through here, this is kind of the process by which the water gets to where we can have it. It's very complicated. They've got to filter out coarse stuff, right? And then sedimentation of smaller particles, that would be getting smaller particles out. And then sand filtration gets out even smaller things. And then we have to aerate it and sterilize it with chlorine. So chlorine can also be an issue when we're looking at things like runoff and pollution and that. So we have to be careful. But you don't have to like be able to describe the whole water treatment process.